we doing? Well, you're good. Good. What questions do you have? Things are all right? All right, let's go through this last problem that was on the notes from last time. And then we'll, pardon me, get into some new stuff. I asked you to look at this from last time as well. So we've got a rational function, 4x squared minus x minus 3 over 2x plus 2. And it's asking all of the same types of questions that we asked last time. So before we start anything else, what did I always tell you to do before you even start this problem? Factor everything, right? So in your denominator, that's pretty straightforward. We can factor out a 2, right? How does the numerator factor? So if you need to use a C method, you can do that. There's not too many options, right, for what these factors could possibly be, because your constant term's a minus 3. So you either need to use a plus 1 and a minus 3 or a minus 1 and a plus 3, right? Not all you got, isn't it? One or the other. I need things to add up in the middle to be negative 1. So what do we need to use? Just not too many cases to try, right? You can try 1 and 4 or 2 and 2 for the x's, correct? If I use 2 and 2, if I tried a 2 and a 2, and I know that the other one has to be 3 and 1, can I get the signs to match right? Because one's going to have to be a plus and one's going to be a minus. Can I get a negative 1 out of that? Because notice you do the 2 times the 1 and the 3 times the 2, you're going to either do a minus 6 and a plus 2 or a plus 6 and a minus 2. That's not going to give me a 1, right? So instead of 2 and 2, we better use 4 and 1. It's just a matter of which order, right? What's it going to be? That works well, yeah. So when you do the 4 times the negative 1, you'll get a negative 4x, and when you do the 3 times the x, you'll get a positive 3x, and that'll add to what we need. Again, if you need to do AC method, that's fine. But these, you should know how to factor these types of polynomials pretty straightforwardly. All right. The reason, again, why we factor is because we want to make sure that nothing cancels out to eliminate something that might be a vertical asymptote, right? That's the whole reason why we factor to start with. Make sure we don't have a hole at some place where it's undefined. That's why you want to factor first. Also, factoring helps us figure out what the intercepts are. So when we look for the x-intercepts, what do we look at? When the top is 0, right? So we have 4x minus 3 times x minus 1 is 0. So what values make that equal to 0? Oh, thank you. What values make that equal to 0? Yep, negative 3 over 4 and 1. So your x-intercepts are negative 3/4, 0, and 1, 0. It's another reason why we like to factor everything to start with is because, again, to figure out your x-intercepts, you want to set the top equal to 0. And then once we have a factor, we can just set each piece equal to 0 and be done with it. How do we find the y-intercept? What do we do? Yeah, plug 0 in for the x, right? In this case, it's probably easier to plug 0 into x into the original, because what do you get when you put 0 into for x into the original one before we factor? Negative 3 over 2. So 0 comma negative 3 halves is the y-intercept. So far, so good? This is the same kind of stuff we were doing last time, isn't it? Just going through the different pieces. For vertical asymptotes, what do we look at? The denominator, right? When the denominator is equal to 0 after we've reduced it to lowest terms. There it goes. After we've reduced it to lowest terms, right? If a common factor cancels out and it's not in the denominator anymore, then we just have a hole at that point rather than a vertical asymptote. Okay. That's why we'll also want to factor it first. So in this case, we look at our factored form. We would set our denominator equal to 0. When does that happen? Yeah, it's just negative 1, right? We could have actually gone to the non-factored form if you wanted to set that equal to 0. Remember, we got a product that equals 0. We would set each piece equal to 0. 2 is not equal to 0, so this isn't getting us anything. It's just this one. So this would be your vertical asymptote here. What about a horizontal one? What do we look at for a horizontal asymptote? Yeah, we look at the top and bottom degrees, right? We look at those leading terms. What do we notice about the degree of the top here? It's bigger than the bottom. So do we have a horizontal asymptote? No. The degree of the numerator is bigger than the degree of the denominator, then there is no horizontal asymptote. So that's different than the other examples that we had. We had, in the first example, I believe the numerator degree was less than, so we had the horizontal asymptote of 0. When they're equal, we look at the ratio of the leading coefficients. This one, top's bigger degree, so there isn't one. What about oblique? Well, remember again, oblique or slant, those mean the same thing. That's the special case. What do we look for oblique? Good. Exactly 1 greater. So is there an oblique asymptote here? The degree is the degree of the top exactly 1 greater than the bottom? Yes. Okay. So how do we find the oblique asymptote again? What do we have to do? Yeah, we need to do a long division, right? Yeah. Okay. So I need to take our 2x plus 1. I didn't leave a lot of room over here. That's all right. We'll figure it out. Move that over up a little bit. And divide it into 4x squared minus x minus 3. And do our long division. Plus 2, thank you. We don't have to do a lot of work. We just need to get the quotient, right? We don't need to worry about the remainder part. It's the quotient that tells us the oblique or slant asymptote. What do we need to multiply 2x by to get 4x squared? 2x. Multiply that through. That's a 4x. And subtract. What do you get when you subtract? So negative x minus 4x. I think isn't what kind of 5? It's negative, right? It's negative 5x minus 3, right? Got to distribute our minus sign through. Yeah. So what do you multiply 2x by to get negative 5x? Yeah, negative 5 halves. And again, you don't have to go through the rest of the steps. We just need the quotient. When we have an oblique asymptote, we just need the quotient. We just need this piece. So your oblique asymptote is y equals 2x minus 5 halves. We don't need the remainder part at all. We just need the quotient. So we can stop there once we have it. All right, so now we're going to use all of these pieces of information to help us get a graph. So what pieces of information do we have? Say it again. Yep, the x-intercepts and the y-intercepts. What were those again? Okay. Okay. Okay, so down here, negative 3 over 2, that's here. Okay. What else do we know? Okay. Vertical asymptote at negative 1. And what else do we know? Yeah, the oblique asymptote that we need to sketch in there, right? So the oblique asymptote was 2x minus 5 halves. So that has a y-intercept at negative 5 halves and then a slope of 2, right? Positive 2. So it's going so this way, and then 2 would be this way. So it's roughly something like so. Just trying to sketch the line in there. Probably extend things down a little bit on this side. So again, we've basically broken up the graph into pieces, and we're going to use the asymptotes as guiding lines for our graph, just like we did in the other ones. It's just that one of our asymptotes is slanted, right? Okay. So again, we basically look at the asymptotes as being our kind of our dividing lines to see what happens on each side of the asymptote. In this case, we just have the one vertical asymptote here, so we'll look on the left, look on the right, and see what happens. So again, we're going to use our asymptotes as guiding lines. So either I have to get close to this line and this line, so it has to go up this way, or it kind of has to make a U shape this way down here. Which one is it? One or the other. It has to go either up or around this way down. But what would happen if it goes up? It crosses the x-axis. Is there an x-intercept over there? No, so it can't go that way. Again, this isn't drawn to scale, but your graph has to go this way, down here. You can find a point or two to see where it needs to be. Plug in something like negative 2. You can help it guide it a little bit. But again, that's the basic shape. It has to do a U kind of shape down at the bottom. It can't go up, right? If it went up, it would cross the x-axis. We would have found an x-intercept. We did not. Okay? So it has to go the other way. What about on the other side? Again, you've got two choices. It either has to do a U shape this way, or it has to go this way, kind of. Right? Does it do this one? Does it go this way? No. Again, because why? Yeah, there's no x-intercept there, right? The points are telling us the other one, correct? So it has to come down, turn around, and go back up. But a little bit smoother than that, though. So again, we're looking at those vertical asymptotes as kind of a dividing line and breaking it into pieces, right? Either went up or went down. We decided it had to go down because it didn't cross the x-axis. Same thing on the other side. What questions do you have on that? So you've got examples of all three of them, how to find the different things. Again, it's this rough sketch kind of idea that we're going to be looking at, trying to be able to generate. Go ahead and go on to new stuff. All right, so in the next section, we're going to look at polynomial and rational functions again, but looking at solving inequalities. This is a skill that pops up in calculus in particular. So the first thing that we need to talk about in this particular section is the idea of a function being what we refer to as continuous. So, pardon me. Before I go to that definition, let's go back to those examples that we looked at, just the pictures, not any of the work. In particular, let's look at this one to start with. Notice that this graph, if I try to draw the graph, I can start here, not lift up my pencil, but what happens when I get to that asymptote? Well, I have to pick up my pencil and then go to the next piece and draw it, right? And then I get to that asymptote, I can pick up my pencil, draw that, right? So what we say here is that was -3, that was at 1. We would say the function is not continuous at those values, at x equals -3 and -1. So notice that our kind of intuitive definition of continuity is that when you draw the graph, I can do that without lifting my pencil. There's no break in the graph. There's no hold. Okay. Notice that in the next example, same idea. I can draw the left-hand side without picking up my pencil, but when I get to that asymptote, I have to pick up the pencil, go to the other piece, and keep going, right? Notice that in all of these examples of the rational functions, everywhere you have that asymptote, you're going to have that kind of break in it. There's going to be a discontinuity there, a place where it's not continuous. So let me go back over to my notes. So roughly speaking, we say a function is continuous if you can draw the graph of the function without picking up your pencil. That's basically the rough idea of being able to have a continuous function. Now notice for rational functions, the only places where we picked up our pencil were where the function was undefined, right? When we hit those asymptotes, we had to pick up our pencil and then go and draw the next pieces. Remember back to when we did polynomial functions and did those kind of rough sketches on there. When you drew those rough sketches for polynomials, did you have to pick up your pencil to draw those? Or could you go from left to right nice and continuously? Yeah, you do it continuously, right? So notice that for polynomials, they're going to be continuous absolutely everywhere. You're not going to have any breaks. Rational functions will be continuous everywhere they're defined. If it's undefined, then it's not continuous. Okay. And we'll focus more on that here in a minute. Right. Another concept that pops up in this particular section that I don't think is actually used anywhere, except for the definition is in here, is the idea of being a smooth function. Right? So my best example that I can give you of a function that's not smooth would be absolute value of x, not smooth everywhere, I should say. What does your absolute value function look like? It's a v, right? Do you see a point on that graph where it might not be considered smooth? At 0, where it's got that sharp corner there, right? So absolute value of x here is not smooth at x equal to 0. And again, that's because of the sharp corner. Okay. There's a couple of other notions of something being not smooth. Well, it certainly can't be smooth if I don't even have a point there. So if it's not continuous at a point, it can't be smooth. But there are a couple of other examples. Remember what cube root of x looks like? Remember what cube root of x looks like? You remember what x cubed looks like? X cubed goes like that, right? Cube root of x is its inverse. It's on its side, right? X cubed looks like so. Remember that, draw this off to the side here. X cubed goes this way. Let's review a little bit of the stuff that we talked about in the last from the last exam. Has an x-intercept at 0 here. What's its multiplicity? What's the multiplicity of the 0 that's at 0? It's 3, right? Because it's x minus 0 cubed, right? It has multiplicity 3. So does it flatten out at that 0? If the multiplicity is bigger than 1, it flattens, right? So it's flat there, correct? All right. So this function is flat at 0. Another way to think about it is it's horizontal at 0 instantaneously, but it's horizontal at 0. The cube root of x is the inverse, right? The cube root is the inverse of x cubed. Remember, inverses change your roles of x and y. What happens to a horizontal thing if you flip-flop x's and y's? Horizontal becomes vertical, right? So, ever so briefly, cube root of x becomes vertical there. We refer to that as a vertical tangent, and this is also not smooth at x equal to 0. We refer to that as a vertical tangent. That's a calculus concept. But that idea is that it's not smooth at that particular point. Okay. So if you get sharp corners or if you get vertical tangents, you get things that are not smooth. So a function is smooth, roughly speaking, if the graph has no sharp corners, no vertical tangents, and by default, and is continuous. So, I mean, graphically, it kind of makes sense what you mean by smooth, except for maybe that vertical piece, right? If something's going to be nice and smooth, you shouldn't hit a corner. You shouldn't hit an edge type of thing, right? That's the idea. All right. Why do we care? Good question. Why do we care? All right. So the first thing that we care about is looking for zeros. And that's what this intermediate value theorem idea comes along. We've spent a lot of time looking for zeros, looking for where a function crosses the x-axis. We're looking for x-intercepts, right? We've spent a lot of time doing that. Unfortunately, not every function is nicely solvable, right? The ones that we've done, we found maybe some rational roots, or we use quadratic formula, or you were given a complex zero so you know what another zero is. Not every function is nice that way. Life doesn't always work out nice, right? So sometimes you want to find x-intercepts or find zeros, but you have to approximate them. Okay. So the intermediate value theorem gives you a little bit of a way to approximate zeros. So here's the idea. Let's draw the picture, and then we'll finish off the statement. Notice that it says that we want a continuous function. So I draw it without lifting my pencil. And f of a and f of b have opposite signs. So just to draw a picture here, I have an a and a b. F of a and f of b have opposite signs. So maybe f of a is positive. So it's above, that point's above the x-axis. And then f of b is negative, so it's below the x-axis. Okay, that's the setup. I've got 1 point above the x-axis, 1 point below the x-axis. This is the setup for the theorem. Okay. The idea is, what happens if I try to play connect the dots? I have a continuous function, so if I start drawing the graph, I'm not allowed to lift my pencil. If I go from here to here, what am I going to have to cross? The x-axis, right? Somewhere, no matter how I draw it, I could try to draw it this way. I cross the x-axis, right? I could try to draw it this way. I still cross the x-axis, right? No matter how we draw it, we're always going to cross it, okay? So that's exactly what the intermediate values theorem says. Then there exists a number C in between A and B such that, f of C is equal to 0. Basically, your A and your B are trapping a value that is a 0 for the function. It doesn't tell you where it is, it just tells you it's in between two things. Now what you can do is you can use this to kind of shrink where it is and start getting approximations that are better and better. That's actually referred to as the bisection method for approximating zeros, which is one of the first methods for trying to approximate things. Approximation is a big deal, by the way. It's what your computers and calculators do for any numeric computation. Well, not any. Most numeric computations. It approximates. All right. So let's see what we mean. Let's put this in action. F of x is this polynomial, x to the fourth minus 2x cubed plus 10x minus 25. Polynomials are always continuous, absolutely everywhere, okay? There is no place where the function is undefined. There is no place where the function's undefined. And when you draw the graph of any polynomial that we've seen, it's nice and smooth and no holes, right? Maybe for a fourth degree one in this case, it might go down and up and down and back up again, but there are no holes, no sharp corners. Okay? All right, so here's how you use the intermediate value theorem. It says show that it has a 0 basically in between 2 and 3. All right, so what you do is you plug in 2 and you plug in 3. Oops. 2 times 2 cubed. So you plug in 2 everywhere for x. What do we get when we do that computation? Well, 2 to the fourth is 16. This is basically another 2 to the fourth. So I'm doing 16 minus 16 gives me 0. Plus 20 minus 25 gives me negative 5. Assuming I did my arithmetic correctly, which is less than 0. Also put in 3. 3 to the 4th is 81. 3 cubed is 27 times 2 gives me 54. 81 minus 54 is 27. I'll do the minus 25 first. That gives me 2. And then plus 30 gives me 32. Which is greater than 0. That's step 1. Plug in the endpoints of the interval you're given. Okay? Is there a sign change? Yeah, this one went from negative to positive, right? F of 2 is negative, F of 3 is positive. Okay? So they have opposite signs. So since F is continuous, it's a polynomial, so it's continuous. F of 2 is less than 0, and F of 3 is greater than 0. The intermediate value theorem gives us a number C between 2 and 3, so that F of C equals 0. And that's exactly what we mean by a 0, right? You plug the number in, you get 0 out. Hence, the function has a 0 in the interval from 2 to 3. So, in order to be able to use the intermediate value theorem, you need to make sure your function is continuous, which in this case is a polynomial. Polynomials are our friends. They're very, very nice functions. So nice, in fact, that when you have unfriendly functions, you approximate them with polynomials. Okay? So the function's continuous, and you have a sign change. If you have a sign change, then there had to be a 0 in the middle. Now again, the intermediate value theorem doesn't tell you how to find the 0. It just says that there is one. So a logical guess for where it may be would be right directly in the middle. You might try 2.5. Right? Might try 2.5. Then see if you have another sign change. And that shrinks your interval down by a half. You can do that again, find the midpoint, shrink your interval down by a half, and so on, and you get an approximation for the 0. Spreadsheet works really nice for that, by the way. So it's a way, this intermediate value theorem gives us basically a rudimentary way to approximate zeros. Now, we're not going to do that. We're just going to check that there is a 0, but that's what this is used for, is to approximate zeros. So how would you attack the next one? What would you do first? Good. Plug in 0 for x and plug in 1 for x, which is great because I've got a more complicated function than I had before. But putting in 0 is pretty easy. What do you get when you put in 0? 420, which is certainly positive, right? When you put in 1, notice all those x's just become 1, right? 1 to the 5th, 1 to the 4th, all of those are just going to be 1. So you get 8 minus 68 plus 160 plus 82 minus 652 plus 420. Anybody actually type that in the calculator? Negative 50. And in particular, what we needed that to be is negative, right? F of 0 is positive and F of 1 is negative. That's the whole thing we're looking for, right? The value, not important. The sign of the value is, right? We need a sign change, right? Okay? If they were both positive, it wouldn't tell you anything. If they were both negative, it wouldn't tell you anything, right? Why doesn't it tell you anything if they were both positive or both negative? Well, look at your graph. If they were both positive, maybe you crossed it, maybe you didn't, right? Does that make sense? Right? Maybe you crossed, maybe you didn't. Okay? That's why you have to have a sign change. If the sign doesn't change, you don't know if it crossed or not. It could have turned around before it got to the x-axis, or it could have crossed the x-axis, turned around, and crossed back again. Right? So you just don't know. All right. So then again, since we have the sign change, the last statement is always the same. Since f is continuous, f of 0 is positive, and f of 1 is negative. We have that sign change. The intermediate value theorem, which a lot of times we abbreviate IVT, just so we don't have to write so many letters. Intermediate value theorem gives us a number C between 0 and 1, so that f of C is equal to 0, hence the function has a 0 in the interval 0 to 1. The last are just the words telling us what that means, right? It's just telling us that since we had a sign change, we had to cross the x-axis in a long-winded math way. That's what it says, right? Since we had a sign change, we had to cross the x-axis. Again, finding zeros of functions is hugely important, okay? This particular theorem isn't telling you exactly where the zero is, but it's giving you a range in which to look, right? It's giving you a starting place. You might want to do more work to get a better approximation, but right now we've got it tracked. Well, we have one of them tracked. So it gives you a place to start looking. And there's lots and lots and lots and lots and lots of different applications where you need to be able to find zeros of functions. Okay. Questions on that at all? All right. Let's see how else we put this into practice. Let's look at the next example, which looks like I just majorly switched gears. All right? Okay. But what type of object do I have on the left-hand side of the equation? What kind of a function is that? It's factored, but what kind of function do we have? It's a polynomial, right? Agree? It's a polynomial? Okay, cool. Do you know where that polynomial crosses the x-axis if I graph it? Yeah, it's factored, right? I know where it crosses the x-axis now. Pardon me. As a matter of fact, we even talked about how we could sketch such a thing, right? Using multiplicities, using end behavior, right? Did all of those kinds of things. Okay. Notice that where the polynomial is equal to 0 is the only place where it can cross the x-axis, right? It can't go in between. The only places where it can cross the x-axis is at -5, at 1, and at 4, right? That's the only place where it can go, right? So let me think about this for a second in terms of the graph, and then we'll translate it over to how we're going to solve this type of problem. What degree did this polynomial have? 4, right? Leading coefficient will be 1. So the degree 4 tells us that your tails point same direction or opposite direction? Same direction, and since it's a positive leading coefficient, they both point up, right? We've got zeros at -5, 1, and 4. I'm not going to worry about the y-intercept because I don't really care. I'm only caring about the x-intercepts here. Okay. Function comes down to x to the negative, or x equals -5. It's going to flatten. Is it going to cross or turn around? Turn around because it's even, right? So it's going to go back up and then it'll cross through, and go up. Right? Roughly speaking, that's what it looks like without worrying about the vertical scale. We agree? Yeah, this is what we did in the last test, right? Right? Okay. All right, so notice that this particular problem is asking you, when is the polynomial greater than or equal to 0? Or when is the output not negative, positive or 0? You can tell me that now from the graph, can't you? Yeah. It's positive here, it's 0 there, but it's also positive here, and it's positive there, right? So we can actually see that, correct? In particular, once again, I want to mention, these are the only points where this thing can cross the x-axis. We don't have any other places where it can cross, right? So for example, it cannot cross anywhere between -5 and 1. When we put in 0, we would get a positive number out. Well, if I put in 0 and get positive, I know that everywhere in between -5 and 1 is going to be positive. Because it can't cross the x-axis in between those two places because the function's continuous. And we found the only places where it crosses the x-axis, right? We can't jump. Okay? Likewise, if you pick a number in between 1 and 4, say 2, and plug it in, I get a negative value. Well, then it has to be negative for that entire interval. Okay? So here's how we're going to solve these types of inequalities. And this goes back to that intermediate value theorem. So the first thing you're going to do is move everything to one side. That seems familiar, right? You've done this any other time that you've tried to solve an equation that involves a polynomial, right? Move everything to one side so you have 0 on the other. What's the next step when you try to solve an equation? If you move everything to one side and get 0, what do you do next typically? It's that dirty 6-letter F word. Factor, right? That's the next step, isn't it? So factor the polynomial. Okay. Factor and find the zeros. Now, did I have to do either of these two steps in this problem that I gave you? No. Everything was already on one side, and it's already factored. Now, if you look at the next example, you're going to need to do 2 steps, all right? Those 2 steps. All right. So 3, we're going to what I like to call make a sign chart. So here's how we're going to make a sign chart. I'm going to make a number line because all I really care about is what we read off the graph a minute ago. Make a number line, put your zeros on the number line. In order, the number line. Don't mix around your order. Okay. Right. This now divides your x-axis into 4 distinct pieces. But again, these are the only 4 numbers, try that again. These are the only 3 numbers where the function can possibly change sign. Those are the only places where we actually hit the x-axis, right? Now do what I was talking about earlier. Find test points. In each of the intervals. So there's an interval that's everything less than -5. There's an interval between -5 and 1, interval 1 to 4, interval 4 and onward. Let's pick something that's less than -5. Doesn't matter what it is, just pick something. -6, sounds good to me. Over here, between -5 and 1, I would always pick 0 if you can. Over here, the smaller the better probably, so I'll pick a 2. And over here, I pick 5. Again, just smaller the better. Doesn't matter. It literally does not matter what number you pick as long as it's in the interval. Okay? All right. We're going to plug these numbers into the function. Okay? So the next step will be plug these into the function. You don't have, by the way, you don't have to write out all these words every time. But I am going to put these numbers into the function and figure out what we get out. Okay? So we'll compute f of negative 6, f of 0, f of 2, f of 5. Take your test points, plug them into the function. Now, I'm going to actually calculate the values for this one, but we don't really need the values. We just need what the signs are, whether they're positive or negative. Okay? Put negative 6 in, we get negative 1 squared is 1 times negative 7 times negative 11. Get a positive 77. I did that right? F of 0 is 25 times negative 1 times negative 4. You get positive 100. Put in 2, we get 49 times 1 times negative 2, so we get negative 98. If I'm doing my arithmetic correctly. So again, I don't care what the value is. I just care whether it's positive or negative. So in a minute, I'm going to go back through this and not pay any attention to what the actual numbers are, just whether they're positive or negative, which is what I would expect you to do. Okay. Put in 5. You get 625 times 4, which is what, 2,500? I think we get 2,500 in that case. Again, do not care what the actual value is. All we care about is if the function is above the x-axis or below the x-axis. Okay? So I could have done the exact same thing I just did, but not worried about the values. If you put in negative 6 in for x, you get negative 1 squared. Is that positive or negative? Negative 1 squared is positive, right? So you get positive for this term. Negative 1 minus 1 is negative, negative 6 minus 1 is negative 7, but it's negative. And that one's also negative. Positive times negative gives you positive. And this is what I mean by the sign chart. Put a positive here. And again, what did I do? Positive times negative times negative. What's the next one going to be? When you put in 0, you got positive times negative again, right? Which makes it positive. The next one, put in 2. That's positive because it's squared. That's going to be positive or negative. Positive, that one will be negative. Positive times negative gives you negative. And then finally, the last one. First one is positive. That's going to be, put in 5, that's going to be positive. Put in 5, that'll be positive. And all we care about is whether it's positive or negative. Okay? Now look at your problem. Answer the inequality. Are you looking for the positives or are you looking for the negatives? Because? Yeah, you're the greater than or equal to 0, right? We're looking for where it's positive and 0. So what interval does this one correspond to here? Good. And we'll put a bracket since it's equal to. Well, hold on. I'll write it this way to start with. The next interval is good. And the next interval is, so 1 to 4 though is negative. So do we want that one? No. So the last interval will be 4 to infinity. Can we write this one right here a little bit shorter? Yeah, you can just write it as negative infinity to 1 because the 5 overlaps, right? Because we had closed brackets. If it were open brackets, you couldn't do that. It has to be closed brackets for that one. All right, So our final answer would be that one. Notice again, we're looking for the positives because it says it's greater than or equal to 0. If you look at the next example, which we're not going to do since we're out of time, if we move everything over to one side, I would move everything to the left. In that one, when you make your sign chart, you'll look for the negatives. All right, we'll do a lot more of these on Monday. Have a good weekend.